Okay, the purpose of this lecture is to analyze the block diagrams associated with both feedback and feed-forward control systems. So let's start with writing the open loop block diagram for our saline production facility. So the open loop block diagram is just the bare process without any control system involved. And it's sort of what nature gives us. So we can design a bit around nature by, for example, changing the volume of the tank. But for the most part, we obviously cannot violate the laws of physics, for example, for how Q and W affect C. So this is what nature gives us. So there are two inputs to this process, Q star. So that's the flow rate of water in deviation form, and also written in the frequency domain. And then there's a transfer function GQ of S that determines the dynamics of how Q star affects how salty the water is. But this is not the only input that affects C. So W affects C as well, right? So this is just one contribution that determines C, how salty the water is. There's another contribution from W, and that's the flow rate of salt. So we'll draw this one coming up. So here's the transfer function for the dynamics of how W affects C. And then incoming into that transfer function box is W star. So here we have two inputs, and both of these add together to give the output C. So I'll decorate this with Q. This is the contribution to C by Q, and this is the contribution to C by W. So we can see C star equals CW star plus CQ star. So how salty the water is coming out of the tank is determined by a contribution from W. Well, I should circle this because this is the contribution from W, and a contribution from Q. And indeed, we can write, just from looking at this block diagram, C star is GW W plus GQ Q. Right? And that's what we derived before in our previous lecture when we reviewed the development of dynamic models. So this is the open loop block diagram. This is not a closed loop. You can contrast it with what we'll derive later. And think of this as what nature gives us. We can't change the laws of physics. How salty water is based on how much salt you put into a tank. You can't change that. But what we can do is outfit this with a control system that tries to maintain C, how salty the water is, near its set point. So this is the sort of setup for our control scheme. So we wish to maintain the outlet concentration of the set point. That tells us that it is a controlled variable. So I'll highlight this. So the control variable must be C because we seek to maintain it at a set point. However, the size of the incoming salt granules, it's highly irregular, and the incoming mass flow rate of salt W is highly variable. So in fact, we can highlight this. Incoming mass flow rate of salt W is highly variable, and that alone tells us the disturbance variable is W. Okay, and to compensate for these changes in W and to maintain the salt concentration at a set point, we have a pneumatic control valve on the incoming water line, and it allows us to adjust the flow rate of Q to compensate for these disturbances. So Q is the manipulated variable here. Okay, so we'll draw these up here. So this is the disturbance variable. And this is the manipulated variable. So the idea is when the disturbance variable, which we can't control, fluctuates or varies, it will in turn affect C through its contribution here, right? But the idea is to manipulate Q so that this cancels out CW, it counteracts the effect of CW, and maintains C star at 0, which means that C is near its set point. That's the idea behind control theory. So, in a feedback control scheme, let's consider outfitting this with a feedback controller. Remember, in a feedback control strategy, we measure the controlled variable. So here we would measure C. And then we would adjust the manipulated variable and adjust Q based on our measurement of C. So let's draw a little salt concentration analyzer here. So this is a composition analyzer. And it's a sensor that determines the concentration of salt, right? And this sensor outputs a milliamp signal. So it's the salt concentration, but a milliamp signal is the measurement of it, right? And this goes into a feedback controller. Okay. And we also feed in the set point. So the set point for the concentration of salt. And then based on the measurement and the set point, the feedback controller computes the error. Based on that, it outputs a pneumatic signal, a certain pressure of air, P. We'll put slashes through here because this is a pneumatic signal. Similarly, this dash signal means it's electrical. And this pneumatic signal pushes on the diaphragm of this control valve and adjusts the flow rate of water, Q. Let's do a couple of thought experiments. If the concentration of salt is greater than the set point, which means colloquially it's too salty, what the controller should probably do is increase Q, right? Because then it would dilute the solution. So this will dilute the solution, and in turn, it will reduce C so it can become closer to the set point. On the other hand, if the concentration of salt is less than the set point, so that means it's too dilute, colloquially, then what the controller should do is decrease Q so we can concentrate the solution and bring it closer to its set point. So those are two examples of how we can counteract disturbances in W that cause C to be greater or less than the set point. So now let's write the closed loop block diagram of this process under feedback control. So again, let me color these according to which is the disturbance and which is manipulated to make it clear. So that's the disturbance variable. And then the manipulated variable is green. So this is manipulated. So to really abstract the block diagram, we can simplify it. So what we can do is have our controller here. So the controller has a transfer function g of s associated with it. And this is up to us as engineers to design. So this is the controller. And I'll put a little heart next to it because it's really the heart of process control. And this is what we can design. And we'll learn to design this in this class. And the controller is fed the error, which is the difference between the set point. So here we have our set point. And the actual value or the measured value of the concentration of salt. So that's why it's called feedback control. We take a measurement of the controlled variable. We'll make this red. So this is our controlled variable. So we measure our controlled variable. And later on, down here, we'll have a sensor, which might hide dynamics, but there's a sensor here. And it measures the controlled variable, feeds it back, and then based on the set point, they compare them. This is the comparator. Let's see, we'll use a different color. This is a comparator because it compares the set point with the actual value of C. Computes the error. So this here is the error. And this is the error. And then based on the error, the controller makes a decision as to how to manipulate a variable to compensate or counteract for the effect of the disturbance variable on C, right? So here's your C sub W, and here's your C sub Q. So this is something you can't control, right? But the controller wants to make C sub Q cancel out CW to maintain C star at 0. Okay? That's the idea behind feedback control. So, what does the feedback control law do? Remember, it takes as input the E. So first of all, it's encapsulated in this controller transfer function GC of S. So what it does is it takes as input E, which is the error signal, and it outputs the manipulated variable. So it tells the manipulated variable what to do. So it's an abstraction because actually we have a control valve in here, right, which then manipulates Q. But this is a simplified block diagram. It's good to start with this. We'll make it more complicated and realistic later. So in words, it specifies how to change the manipulated variable based on the error. And it can be a function of the history of the error as well, not just the current error. And that's in PI control for integral. So it's really important to know process dynamics for successful feedback control so that we can design this control law to keep C of t near its set point. So we can think of minimizing a functional. So a functional is a function of functions. So we can minimize for all time the set point minus the actual concentration, and we'll square it so there are no cancellations to make it 0. We want to minimize this integral, and what's nice is as engineers we have the freedom to design this control law to make this functional small and keep C near its set point. Okay, so in feed-forward control, what we do is we measure the disturbance variable. And the disturbance variable here is W, and still we adjust the manipulated variable on that basis. So we adjust Q on that basis. So I think before we had a camera here, right? So this is a camera. So here's your camera. And you can imagine it looking down, whoops. You can imagine the camera looking down on the salt, right? It analyzes the size of the salt granules. And then it outputs a milliamp signal of what the flow rate of salt is. And that's fed to a feed-forward FF controller. As well as a set point. And then this feed-forward controller outputs a pneumatic signal on the control valve, again adjusting the flow rate of Q. But now it's on the basis of a measurement of the disturbance variable. So a couple of thought experiments. If W is greater than W bar, the steady state value, the nominal steady state value, then, i.e. if W is higher than usual, what the controller should probably do is open the control valve to dilute the solution. Because this jump in W, we anticipate that it's going to make it more salty. And if W is less than W bar, what it should do is close the control valve because we would over dilute the solution otherwise. To concentrate the solution. And so both of these are in anticipation of how W star, the change in W, will affect C. So both of these. In the first, we anticipate if W jumps above its steady state value, it's going to make it more salty. In the second, we anticipate it will make it less salty. So we take action. So now let's draw what the feed-forward control loop looks like. So now, instead of measuring the controlled variable like we did before, so we'll highlight these again. This is controlled. We're not going to measure that this time. Instead, what we'll do is measure the manipulated variable. Sorry, measure the disturbance variable. Okay, so here, this is fed to the feed-forward controller. Right? Oh. So measurement of the disturbance is fed to the feed-forward controller, as well as the set point. And then the feed-forward controller then tells the manipulated variable what to do. So this is the manipulated variable. So again, here, there is usually a control valve because the feed-forward controller outputs a pneumatic signal to the control valve, but we're simplifying it for now and pretending the feed-forward controller directly tells the manipulated variable what to do. Whoops. So this is a simplified block diagram of the feed-forward controller. And I should put a transfer function in here. So this is the control law, GC. And this is the FF controller. So let me make sure I did the same there. Yeah, so we'll call this FB controller to distinguish it for feedback controller. So what the feed-forward controller law, what the feed-forward control law does is it takes in the measurement of the disturbance variable, And based on that measurement, it decides what to do with the manipulated variable. So it makes a decision. Outputs Q, the manipulated variable. And it's extremely important to know process dynamics for feed-forward control. And that's because we need to know both how W affects C and Q affects C to know how to adjust the manipulated variable. So we need to know how W affects C and how Q affects C. So we must know to take the appropriate counteraction to eliminate the effect of the disturbance. On the controlled variable. It totally makes sense. So you know the disturbance is coming, then you need to anticipate how that disturbance is going to affect C, and then you also need to anticipate how the manipulated variable is going to affect C. Not anticipate, but you need to know how it affects C in order to know what to do to the manipulated variable. So you need a really accurate process model for feed-forward control. Okay, so you can see these are both closed loops, right? See the loop here? Closed loop. See the loop? And you also see a loop up here, right? So these are closed loop block diagrams. And this one, there is no such loop, right? So it's an open loop block diagram. This is what nature gives us. Okay, so finally, two more things, and then we're done. Regulatory versus servo control objectives. In regulatory control, the objective is to reject, so in 2 words, disturbance rejection. That's our objective. And then more specifically, what I mean by that is to eliminate the effect of the disturbances on the controlled variable. On the other hand, in servo control, our objective is different, and that is set point tracking. Okay, more specifically, if we change the set point of C, say we want to make the salt water more salty. Because the customer demands higher salt in the saline solution. Then what we want to do is coax the controlled variable which is C here, to quickly reach and maintain this new set point. And interestingly, there's often a trade-off between controller performance and regulatory and servo control. So these are two different objectives. So one is when we want to change a set point and make the controller change the manipulated variable so as to reach that new set point. And the other is to reject the influence of disturbances on the controlled variable. So regulatory versus servo control.